Hess's law is just a way where you can add reactions together to make a different reaction. You're probably more familiar with doing this with algebraic expressions, so we'll use that as an example first. So, for example, if you wanted to add 2x minus 3y equals 5z to 1z plus 2y equals 4x, you know that if they're on opposite sides of the equal sign, they can cancel each other out or just subtract from each other. So here we have 1z and we have 5z on the other side, so that means we have 4 left over. We have 2x on one side of the equal sign and 4x on the other side, so that means we have 2 left over. And then the minus 3y and the 2y are going to combine together to make y equals 4z plus 2x. This first example is an actual reaction equation. You're given that your target, the PCl5, going to PCl3 plus Cl2, and you want to find the heat of reaction for this particular reaction. And you're given two reactions, the P4 plus 6Cl2, giving you 4PCl3, and 4PCl5 going to P4 plus 10Cl2. And you have the heat of reaction for each of these. So you can combine these two reactions together so that you can make your target reaction, and by adding the reactions together you can add the heats of reaction together to figure out what the heat of reaction is for your target. So first thing I like to do is I look at the first part in the target and I say, alright, PCl5, and then I look at the given reactions and I see that I have PCl5 on the proper side of the arrow, but there's too many of them. So what I want to do is I want to multiply the reaction equation by 1/4, so I'll end up with 1 PCl5, which means I have to multiply the heat of reaction by 1/4 as well. So I'm going to go ahead and do that. So we end up with PCl5 going to 1/4 P4 and 10/4 Cl2. Go ahead and leave it as an improper fraction for right now. Then we're going to look at the next one. We want to find PCl3 on the right-hand side of the arrow by itself. And then we see that it's on the right-hand side of the arrow, but there's too many of them. So we have to multiply by 1/4 again, which means we have to multiply the heat by 1/4. So I'm going to go ahead and write that down. So we have 1/4 P4 plus 6/4 Cl2 going to 1 PCl3. So now we've used that reaction, we've used that reaction. You'll never be given more reactions than you actually need, so we're going to go ahead and figure out what's left over. So we have 1/4 P4 on both sides of the arrow, so we're going to cancel those out. We have 6/4 Cl2 on one side, 10/4 Cl2 on the other side. 10 minus 6 is 4, so we can subtract that out. So we're left with 4/4 Cl2. Nothing else cancels out, so we end up with PCl5 going to PCl3, and 4/4 or just 1 Cl2. So going ahead and doing the math, 1/4 times negative 2439 is equal to negative 610 kilojoules. 1/4 times 3438 is equal to 860 kilojoules. So we add those together, and we get for our answer is that the heat of our target reaction is 250 kilojoules. So let's look at one more example. Here our target reaction is 2CO2 plus H2O gives us C2H2 and 5/2 O2. And we're given the three reactions below. So let's look at this again using a systematic approach. So I like to look at, so we have 2CO2, and we find 2CO2 down in reaction 3, but it's on the wrong side. So that means we have to flip the reaction. When you change the direction of the reaction, you change the sign on whatever heat reaction you're talking about. So I'm going to go ahead and write that over again. So we end up with 2CO2 plus 3H2O goes to C2H6 and 7/2 O2. And that would be positive 283. Let's go on to the H2O. So we got looking for it on the left-hand side. Problem with water is that it's in two different places, so we don't want to mess with that right now. So let's look instead at C2H2, and it only shows up in one place, in reaction 1, and again it's on the wrong side, so we're going to flip that one, which means we change the sign, and I'm going to go ahead and write that over again. So we have C2H6 going to C2H2 plus 2H2. And since we changed the direction of the reaction, we have to change the sign, so we end up with positive 94.5. So now let's look at what's left over. If you look down here in the different reaction equations, we have two H2s, and H2 does not show up at all in the your target reaction. However, it does show up in the last reaction that we have not used. Again, it's on the wrong side and there aren't enough of them, so we're going to flip it and multiply by 2. So now we have a negative 71.2 times 2. So now we have 2H2 plus 1O2 going to 2H2O. And then when you go 2 times negative 71.2, that gives you a negative 142.4. Now we're ready to cancel stuff out. So we have 2 waters on this side, 3 on the other side, so that leaves us with just 1. We have 2 H2s on the left side, 2 H2s on the right side, so that cancels out. We have C2H6 on both sides, so they're just going to go away. They cancel each other out. We have 1O2 and 7/2 O2, so we're going to make that a 2/2 O2, just so it's easier to see. So 7 minus 2 is 5, so that one goes away, and we're left with 5/2 O2. We're ready to add them up, so 2 CO2 plus 1 water is going to form 1 C2H2 and 5/2 O2, which is the same as our target reaction. Since it's the same, we can now just add those together, and you end up with a heat reaction for our target that is 235 kilojoules.